Welcome friends. Let us continue to study heat engines on my YouTube channel. Kindly like, share and subscribe my YouTube channel. The topic included in today's lecture is Rankine cycle, construction and working of Rankine cycle and efficiency of Rankine cycle. The limitation of Carnot cycle, that is vapor as a working fluid. Mixture of water and steam is to be compressed in compressor, which is practically very difficult. Superheating of steam is not possible and therefore it affects the life of turbine. Carnot vapor cycle is not practically used in thermal power plant. So impracticalities associated with the Carnot cycle can be eliminated by one thing: superheating the steam in the boiler and condensing the steam completely. It means converting the steam or the mixture of water and steam completely into water in the condenser. And the modified cycle is known as the Rankine cycle. It is the ideal cycle for thermal power plant. Means this cycle is utilized in thermal power plant. Trained as a civil engineer, William Rankine has invented the Rankine cycle. This one is the, you can say, layout how the electricity is produced. Now let us see or study the component of Rankine cycle. Now first component is boiler, in which heat is supplied to the water and converted into the steam. Second one is the turbine. So the steam generated in the boiler is entered into the boiler and the turbine is rotated. So we are getting the work done. Now the exhaust steam from the turbine enters into the next component, that is the condenser. Now in condenser, the exhaust steam of turbine, which is a mixture of water and steam, that is wet steam, is completely converted into liquid, and in the condenser heat is rejected. So it is the condenser is working as a heat sink. And lastly, the completely converted mixture of water and steam into water after condenser now enters to the pump, where the work is provided to the pump, and with the high pressure the water again enters into the boiler. So this one is the, you can say, flow diagram of the Rankine cycle. This one is the another sketch of the Rankine cycle, where we have this steam generator or a boiler where heat is supplied. Next one is the turbine, where we are getting work output, and due to that we get the electricity. Then after, exhausted steam from the turbine enters into the condenser, where heat is rejected and the mixture of water and steam is completely converted into water after condenser. And that water is now entered into the pump, where work is supplied to the pump, and due to that high pressure water again enters to the steam generator, that is the boiler. So now let us study the each component one by one and draw its PV diagram. So this is boiler, where the heat is supplied, and at point 1 it is a water, and point number 2 we are going to get the steam. And 1-2 process is known as the constant pressure heat supply. Now if you remember the Carnot vapor cycle, process number 1-2 takes place in a boiler, but that process was, can anybody say? Yes, it was the reversible isothermal heat supply, but here it is constant pressure heat supply. Next component is the turbine, in which steam expands and we are getting the work done. And 2 to 3 process is known as the reversible adiabatic expansion. This process number 2 to 3 is same as the Carnot vapor cycle. 3 to 4, the exhaust steam from the turbine enters into the condenser and completely converted into the liquid. And in the condenser, heat is rejected. Now, what is the process name here? It is the constant pressure heat rejection. It means the heat is rejected at constant pressure. Now, if you remember the Carnot vapor cycle, here the process was, yes, it was the reversible isothermal heat rejection. And last process is pump, in which the completely converted condensate, that is water, is compressed into the pump and again entered into the boiler. And that is the process number 421, where work is supplied to the pump. And the process name is reversible adiabatic compressor. It is the same as the Carnot vapor cycle, but in Carnot vapor cycle, they use the compressor. Here they use the pump. Now let us draw the PV diagram. As it uses the working substance which is in two state, so we have to draw this saturation curve. Clear? First component boiler where heat is supplied at constant pressure, and process number 1 to 2. So now the line will be like this, because on y-axis it is pressure, so it will be constant pressure line. This is point number 1 and this is point number 2. So now there can be the three possibilities. One, at point 2, whatever I have you can say sketched here, at that point the steam may be dry and saturated. Clear? That is one thing. At point number 2, it can be wet also. So the point number 2 can be here, that is 2 days also. And at point number 2, it can be superheated also. So it can be 2 days, 2 double days point also. It means whatever the steam is coming out from the boiler, it can be dry steam, it can be wet steam, or it can be superheated steam. And accordingly, we can have three different 2 points. One is 2, dry and saturated, 2 days wet steam, and 2 double days superheated steam. Now that steam now enters to the turbine and gives us the work done. And the process name is reversible adiabatic expansion process. So if it is dry and saturated steam, then the process will be 2 to 3 like this. If it is wet steam, the process will be 2 days to 3 days like this. Now if the steam is superheated steam, the process can be shown by the line 2 double days to 3 double days, and here we are getting work outside the system. Clear? Now the next process takes place in condenser, where the mixture of steam and water converted into totally liquid, or where heat is rejected to the surrounding. Clear? So here, whatever may be the condition, whether it is 3 double days, 3 or 3 days, the heat is rejected from any of the 3 points, and the condition at point 4 is saturated liquid. So it is totally converted into liquid, and at this process heat is rejected. And what the last process? Last process is the pump, in which liquid is compressed, that is water is compressed and again entered into the boiler, where we are required to supply the work to drive the pump. That is the reversible adiabatic compression process. So here it is 4 to 1, where we supply the pump work. So that was the PV diagram for the Rankine cycle. Now let us draw the TS diagram for the Rankine cycle. Again, TS diagram, this one is the saturation curve. Now, first component is the boiler, process number 1 to 2, heat is supplied, and the process name is constant pressure heat supply. Now, as it is a constant pressure heat supply, it will be as it is as we have studied in the steam formation. So here there will be the heating and then converting water into the steam at point 2, that is a dry steam. It can be wet steam also, that is 2 days, or it can be superheated steam also, that is 2 double days. Clear? So at 2 point, dry steam, 2 days wet steam, and 2 double days superheated steam. Then after, it enters into turbine, where we are getting work done. And the process is reversible adiabatic expansion, that is isentropic process. So it will be a vertical line. So if it is dry steam, the line will be 2 to 3. If it is wet steam, line will be 2 days to 3 days. And if it is superheated steam, line will be 2 double days to 3 double days. And we are getting work from the turbine. The next process takes place in a condenser where heat is rejected at constant pressure. And at point 4, we are getting completely liquid. So whatever may be the point at the end of the turbine, whether it is 3 days or 3 double days, after condenser it reaches to the point number 4, that is completely liquid and heat is rejected. And 4 to 1 is the pump, where the liquid is pumped to the boiler and we are required to supply the work to the pump, and it is denoted by the line 4 to 1, that is pump work is supplied. So that was the, you can say, TS diagram for the Rankine cycle. Now let us study the, you can say, the heat content of the steam or a water at different points. So consider it is a boiler where heat is supplied. At point 1, the enthalpy is H1 and that enthalpy is enthalpy of water entering the boiler. At point 2, enthalpy of steam coming out from the boiler. So what is the heat supplied in the boiler? Yeah, so heat supplied is H2 minus H1. Now let us study the next component, turbine. Process is reversible adiabatic expansion. At point 2, enthalpy is H2. At point 3, enthalpy is H3. H2 is equals to enthalpy of steam coming out from the boiler or entering the turbine. While at point 3, enthalpy is enthalpy of steam coming out from the turbine, entering the condenser. And in the turbine, we are getting work output also. So which enthalpy will be more, H2 or H3? And due to that, Wt is equals to H2 minus H3. Now let us study the next component, that is the condenser, in which heat is rejected to the surrounding. Now at point 3, enthalpy is H3, which is enthalpy of steam coming out from the turbine and entering the condenser. And at point 4, enthalpy of water coming out from the condenser and entering the pump. Clear? So what will be the QR, that is the heat rejected? It will be equal to H3 minus H4. And what is the last component? Pump, where we supply the work to the pump, and due to that the water is compressed to high pressure. Now let us see, at point 4, enthalpy is H4, enthalpy of water coming out from the condenser or entering the pump, and H1 is enthalpy of water coming out from the pump and entering the boiler. So which enthalpy will be more, 4 or 1? Yes, it will be 1. So Wp is equals to H1 minus H4. So now let us calculate the net work done and efficiency of Rankine cycle. So net work done equation is Wt minus Wp, or it is Qs minus Qr. So what is Wt minus Wp? Wt is H2 minus H3 and Wp is H1 minus H4. So it is H2 minus H3 minus H1 minus H4. So if you write Qs minus Qr, it will be the same N1, that is H2 minus H1 minus H3 minus H4. It is nothing but the rearrangement of some term. So ultimately it is the same. So W net work done is equals to Wt minus Wp, or it is Qs minus Qr. Efficiency of Rankine cycle. It is work done divided by heat supply. So work done is H2 minus H1 minus H3 minus H4 divided by heat supplied. Qs is H2 minus H1, H2 minus H1. So the answer is 1 minus H3 minus H4 divided by H2 minus H1. And that efficiency of Rankine cycle is known as the efficiency considering pump work. So we can say that efficiency of the Rankine cycle considering the pump work is 1 minus H3 minus H4 divided by H2 minus H1. So you look at the formula, it requires the enthalpy at all 4 points. Enthalpy at point number 1, enthalpy at point number 2, enthalpy at point number 3, and enthalpy at point number 4. So if we know the enthalpy of steam and water at different points in a cycle, then we can calculate the efficiency of Rankine cycle considering pump work. Now let us study the efficiency of the Rankine cycle or the analysis of the Rankine cycle neglecting the pump work. So this one is the, you can say, flow diagram of Rankine cycle, and this one is the TS diagram where we have considered the pump work. That is 4 to 1 here, and here it is 4 to 1 the process also. Now let us neglect the pump work. Means there is no pump. Neglecting pump means there is no pump in the system or in the cycle. So what we can see? We can see that point 1 coincides with point number 4. So 1 and 4 point are same. So you can say here on TS diagram 1 and 4 point are same. So it will be like this. So direct 4 point, now it is connected to the top of point. So this one is the, you can say, modified TS diagram considering the there is no pump in the system, that is neglecting the pump work. So my heat supplied is H2 minus H1, so that is okay. Work turbine is H2 minus H3, that is okay. Condenser heat rejection is H3 minus H4, but we know that H1 is equals to H4, so we can write down H3 minus H1 because now H4 is not there. Or 4 and 1 point are same, so it is H3 minus H1. And pump work, that is H1 minus H4, as we have neglected, WP is equals to 0, or H1 is equals to H4. By using this equation, we can also write down that H1 is equals to H4. Now net work done. QS minus QR or WT minus WP. And it will be H2 minus H3. Because WT minus WP is 0. So WT is H2 minus H3. So it is net work done is equals to H2 minus H3. And the efficiency of the Rankine cycle is work done upon heat supply. Now what is the work done here? H2 minus H3. And what is heat supply? H2 minus H1. So the efficiency of the Rankine cycle neglecting pump work is H2 minus H3 divided by H2 minus H1. It means if we neglect the pump work, we require the efficiency at 3 points only. Point number 1, point number 2, and point number 3. That is the water entering into the boiler, steam coming out from the boiler, and steam coming out from the turbine. If we know these 3 enthalpies, we can calculate the efficiency of the Rankine cycle neglecting the pump work. Kindly ask all your queries in the comment box. Kindly like, share and subscribe my YouTube channel. Thank you.